last class we started the refraction. Okay, let's do these problems. Okay, the first and second, these two problems we have these prism. They are known as prism. Okay, a structure like this, triangular. It is a triangular prism. Okay, and the second also. In second question, one face. This face is silvered. Okay, this is silvered here, so it behaves like a mirror. Okay, I will find for what value of mu, what should be mu here, such that light retraces its path. It enters in this direction, it has to come back along the same path. Okay, for that to happen, what should be mu? Now, this is known as a slab, parallel glass slab. Like this. This is a parallel glass slab, a cuboid-like structure. A cuboid, not like, but a cuboid. Okay. So all the angles are 90 here. Rectangular. It's a rectangular slab. Okay, rectangular. It's also known as rectangular. Rectangular slab. Okay, thickness is d. Light enters here. Angle of incidence is given. Reflection is given. Mu is given. Okay. And we have to find what is net deviation. That means when the light finally comes out from this slab, what is going to be deviation? And we will see some very interesting result. Okay, very interesting. And here I have all the interfaces. All interfaces are parallel. Okay, so these are the interfaces. All the interfaces. We have different mediums. Medium 1, 2, 3, 4. Okay, the interfaces, all of the interfaces are plane and parallel. Light enter here, okay, traveling in one medium here, angle is 45 degree. What will be light here, okay? At what angle the light will emerge into this last medium, mu 4? What is the angle of emergence in last medium, okay? All interfaces are parallel. Prove that light emerges parallel to itself if mu 1 is equal to mu 4. That means if the first and the last medium, if the first medium and last medium, if both are same, then no matter what happens in between here, okay, the light is always going to emerge parallel. Okay, but it will be shifted somewhat. Light is going to come out parallel to this direction. Maybe it will be shifted. Okay, there will be some shift. That is known as lateral shift. That is known as lateral shift. Okay, we will see how to calculate it in this problem. Let's start with this one. Okay, the first one. What it is? It's like this. So I have this prism. So this is the first point where medium changes. So refraction will happen. You see, whenever medium changes, there is refraction. Whenever medium changes, there is refraction. Light enters here at this point. At this point, this angle is given. This angle is 30 degree. So what I will do? First, I will draw the normal. I have to measure all the angles from normal. Okay, this is the most common mistake that we actually make. So I have to worry about this angle. This will be 60 degree. This is point 1. Okay, so we are going to apply Snell's law at point 1. This is mu is root 3. Okay, point 1. Point 1. Okay, I will write this 1. This is mu is equal to 1. If nothing is given, that means it's vacuum or it's air. Okay, so 1 and this is sine 60 is equal to root 3 times sine theta 1. Okay, let's say it is theta 1 here. You see, okay, let's do it like this. This is my original direction of incident ray. Okay, what is going to be theta 1? Angle here. So root 3 over 2 is root 3 sine theta 1. Sine theta 1 is half. Theta 1 is 30 degree. 30 degree, okay, that means this angle is going to be, here this angle is going to be 30 degree. This is 60, this angle becomes 30. 30 degree. This is theta 1. Okay. Now, the light enters into this medium. At this point again, there is change in medium. Again, the medium changes. Okay. So here also, this is point 2. Here also refraction happens. Okay. This is the original direction of light. Okay. I have to draw this normal. Draw this normal here. Now, what will be this value? Okay. What will be this angle here? Okay. So some angles are given 60. Okay. This is 60. This is 60. I don't have to worry about these two angles. I have to worry about them. Okay. It is not required. Okay. Even if I know this angle, this is 60 degree. You see, this is 60. Okay. What is this angle here? This is 60. This whole thing is 60. Okay. That means this is 60. This whole thing is 60. This is 60. So this whole angle from here to here, it will be 60. And this is a normal. You see, this is my normal, N1. This also is normal, N2. This is 90. That means this angle becomes 30. Okay. This angle becomes 30. Okay. Does that make sense? Does that make sense to you? After that, how do we find out? This is 30, this is 30. Okay? This whole angle is 90, this whole thing is 90. Okay, that means angle between this line and this normal, it is 90. Out of that, one angle is 30, here it is 30, that means this angle here, it must also be 30. Okay? Okay? That means this remaining angle from here to here, this must be 60. Or we can also say that this angle here, this angle between this line and this line, this whole thing from here to here, this whole thing is 90. Out of that, one angle is 30. So the remaining will be 60. So 60 here, 60 here. Okay, the third angle here, this becomes 60. If this is 60, then this becomes 30. This becomes 30. Okay, now the light again undergoes a change in medium. At this point again there will be refraction. Again there will be refraction. Okay, what will be angle of refraction or angle of emergence? Let's say. Okay, this is my angle of emergence. Light comes out. Light is going from denser to rarer medium. It is going to bend away from normal. This is my normal. Normal. This is the original direction of incident ray. When the light goes from denser to rarer medium, it bends away from normal. That means this angle is going to be more than 30. What it will be? Can we find here directly? Directly we can find it here. In this case, not in every case, but in this case. Okay. Okay, look at this. Angle in air is 60, angle in glass is 30. Angle in air 60, glass 30. Glass 30, air 60. Glass 30, air 60. Okay, or you can apply Snell's law like this, you are going to get the same thing. Okay, but that's how, that looks like more, okay, beautiful. Okay, a good logic here. Now, so this is the angle of emergence. Okay, I have to find net deviation. Net deviation. First time, this is the first time that, okay, let me make it a clean diagram. Okay, it's like this. So the light is getting deviated twice, successively. Light is getting deviated twice, successively, okay, one after another. There are two successive deviations, okay. This is the first deviation here, this is 60 degree, okay. And this is the original direction. This is the original direction. Okay. Light gets deviated like this. Okay. This is the first deviation. First deviation. Okay. This is delta 1. This is delta 1. Okay. What is delta 1? Delta 1 will be 60. This will be 30 degree clockwise. Delta 1 is 30 degree clockwise. Here again there is deviation. Okay. This is my normal here. Again it gets deviated. This is the original direction. It gets deviated like this. Okay. This is the second deviation. Delta 2. From here we can easily see that delta 2 is going to be, this also is 30 degree clockwise. Both deviations 30 degree clockwise. Now this becomes the net deviation. Okay, this is my original direction of incident ray. Finally, it goes in this direction. So this whole angle, this whole thing is delta. Okay, what it will be? It will be simply delta 1 plus delta 2. It is going to be 60 degree clockwise. Okay, 60 degrees clockwise. That's it. I can also say that this is delta 2. So this angle is delta 2. This is also going to be delta 2. Delta 1, delta 2. Okay. This is an external angle. It will be equal to this plus this. Okay. That also, we are applying two different logic, but we are getting the same answer. You can apply either one. Okay. That's how we do it. Now the next one. Here also I have a prism, but a different type of prism. This angle is 90 degree. This angle is 30. Okay. Let's see what we get. The light is incident normally. It is normal incidence. Okay. Light is incident like this. It is normal incidence. At this point, medium changes. Angle of incidence is 0. It is a normal incidence. Will there be refraction? First question. Will there be refraction for this normal incidence? Okay. The answer is there will be refraction. Because medium changes. The moment medium changes, this changing of medium is known as refraction. Okay. Refraction is transmission. That's it. Refraction is transmission. So will refraction happen? Yes, it will happen. Will the light deviate? Light will not deviate. Okay. In case of normal incidence, there is no deviation. Okay. So the light continues moving in the same direction. There is no deviation. Then it hits this point again. So here again the medium is going to change. So there will be refraction. Here. Now let's find out the angle of refraction. This is 30 degree. This is 90. Okay. That means this will become 60. And if I drop a normal here, this is my normal. This angle is 30 degree. Okay. Apply Snell's law at this point. Okay. This mu is given. Mu is 2. So 2 times sine 30 is 1 times sine theta. Let's say I want to find theta. Okay. So what is sine theta? Sine theta will be 1. What is theta? Theta is 90 degree. Now what does that mean? This is angle of refraction. This is angle in the second median, that is air. Angle is 90. This angle is from normal. It is from normal. That what it means is this is the original direction. Light is going to be refracted in this direction. This is how the light is going to be refracted. It will be refracted along the surface. It's like this. This whole angle, this whole thing is 90 degrees. Okay. This is angle of refraction, the angle in this medium air. It is 90. This is the meaning of 90 degrees. Okay. This was the original direction. Okay. So this is my deviation. This is net deviation. Okay. Or it will be. It should be easy. Okay. This is 60. This also is 60. It is 60 degrees. Okay. Got it? Okay. Let's move on to the next one. Next problem. Okay. Under what condition light retraces its path? This acts like a mirror. Okay. So this one surface is silver. This is known as silvering, or it is painted. Okay. Then it starts behaving like a mirror. It becomes a mirror. Okay. So when light enters, when light enters into this medium, okay, it is going to be reflected from here. It is going to be reflected. Now the light has to retrace its path. It has to retrace its path. Under what condition a light retraces its path? In case of reflection. In case of reflection, okay, light retraces its path if it is incident normally. That means after entering into this prism, the light must hit this surface normally. In that case only it is going to retrace its path. Okay. Now here we have this situation. Okay, this is a mirror. I want this to retrace. Okay. It will retrace like this. Okay. This angle is theta. To retrace, it must hit this surface normally. If the light ray hits this surface normally, in that case it is going to retrace. And whenever light starts to retrace, it retraces its entire path. Okay, so it will come out in the same direction here. It retraces its entire path. Okay, right on this. You have to remember this thing. Keep this thing in mind. Okay, at this point refraction happens. This angle is theta. This is 90 minus theta. So this angle becomes theta here. This is theta. So this becomes 90 minus theta. Okay, this is mu. I will write 1 and sine 90 minus theta is mu times sine theta. Okay, this is cos theta. Cos theta is mu sine theta. What is mu? It is cot theta. Did you get the same answer? Okay, did you get the same answer? All right. Let's see. The next one is very interesting, and it's a standard case. The results we have to keep in mind. The results we have to keep in mind. Okay, let's see what it is. It's a parallel glass slab, also known as rectangular glass slab. All the angles are 90 degree. Rectangular means perpendicular, 90 degrees. Okay. And they are parallel, of course. If all angles are 90, they are going to be parallel. So these two sides are parallel. Light is incident on one surface here. Okay, let's see what happens to this light. Okay, what we have to find? We have to find net deviation and lateral shift. Okay, so let's try to understand both. What will be net deviation? What will be lateral shift? Okay. It's like this. Okay, I have this slab here. Let's say this is my slab. Light is incident at some angle. Let's say it is incident here. Like this. Okay? It is incident in this direction. This becomes my original direction. What is this? Light was coming along this direction. This is my original direction. Okay? Understand this? At this point, refraction happens. Refraction happens because the medium changes. Okay. Let me draw this normal here. Okay. Light enters from air to glass. This is one here, air to glass. It is going to bend towards the normal. This is the original direction. This is normal. It is going to bend towards normal. It will bend like this. It bends like this. Okay? Understood? This angle is given. It is R. Okay? This angle is I. Okay? Here again there is change in medium. Okay? So let me draw one perpendicular here also. Let me draw it here also. Okay. Now if this angle is R, these two normals will be parallel. This is R, this also is going to be R. This is R, this also is going to be R. Now see this connection. I have to apply Snell's law at this point here and this point here. Without applying Snell's law, we can use this beautiful simple logic. Angle in air is I, angle in glass is R. Angle in air I, angle in glass R. Angle in glass R, angle in air I. Angle in glass R, angle in air I. Okay? It is going to be equal to I. So this is my original direction. It is going to deviate. It is going to deviate. And this angle from this line is going to be I. This also is I. That means it is going to be parallel to this line. It is going to be parallel to this line. Okay? This is my angle of emergence. This angle of emergence E is going to be equal to I. This is angle of incidence. This is the final angle of emergence. Okay? From the symmetry, from this simple logic, we are saying that if this E is going to be equal to I. That means these two are parallel. Okay? These two are parallel. This line, the incident light, the final emergent light. That means the light is finally emerging parallel to itself, but it is somewhat shifted. It is somewhat shifted. This is the shift. It is shifted by this distance. Let's say it is equal to delta. What will be delta? Okay, so what will be deviation? Deviation will be 0. There is no deviation. The direction remains the same. Only it is somewhat shifted from its path. It is somewhat shifted from its path. This is known as lateral shift. Lateral shift. Lateral shift. Okay? Let's try to find out what it is going to be. Let's say that this point is A, this point is B here, this point is C, and this point is D. Okay? This angle is R. This angle is going to be equal to I minus R. I minus R. Okay? It's very simple geometry, very simple mathematics. In triangle ABC, okay, I can write cos R is equal to AB over AC. Okay, so AC will be equal to AB over cos R. Cos R. This will be equal to T over cos R. What is T? What is T? T is thickness here. T is thickness of the slab. Okay, now in the other triangle, I want to find this. Okay, so I will look at the other triangle ACD. Okay, triangle ACD. Okay. Delta is equal to CD. This side CD, and this is going to be equal to AC. This is AC and sine I minus R. Sine I minus R. Okay, and that's it. This is my lateral shift delta AC. Okay, so T times sine I minus R over cos R. Okay, I and R will be related by this. Okay, mu. Okay, so 1 times sine I is going to be equal to mu times sine R. Okay, so sine I is equal to mu sine R. Okay, so I can put this relation. I can put this relation in this expression. I can find shift in terms of mu, I and T. Okay, but this also is a perfectly valid expression for shift. This is known as lateral shift. Okay, now the next problem. What is angle of emergence in last medium? Okay, can you find out? The light ray undergoes successive reflection, one after another. One after another. Okay. Look at this, a very beautiful thing. Okay, a very beautiful property here. Let's say that I have this. Okay, so 1, 2, 3, 4. Let's say this is medium 1, this is medium 2, this is 3, this is 4. All of them are parallel mediums. All of them are parallel. Let's say that light enters here at this point. Light enters, or let's say that light enters at this point here. This is theta 1. This is theta 1. Refractive index here is mu 1. This is mu 2. This is mu 3. This is mu 4. Angle in medium 1 is mu theta 1. It bends like this. Let's say that it bends in this direction. This angle is theta 2. Okay. Now, if these two are parallel, understand this. What we are going to discuss, a very beautiful important property. But that will be true only if these mediums are parallel. If these two are parallel, this angle is theta 2. Okay, then this angle here will also be theta 2. This is also theta 2. Okay, this is point A, let's say. Right? This is point A. This is point B where refraction happens, point B. Now, again there will be refraction. The light is going to bend. Let's say that it bends like this. Let's say, okay, it bends like this. Okay, this angle is theta 3 in medium 3. Okay, then here, this is going to be theta 3. Both are theta 3. And finally, let's say that it comes out in medium 4, and this angle is theta 4. This is point C. Okay, let's write the Snell's law at point A, B, and C. Okay, at point A, what is Snell's law? Mu 1 sine theta 1 is mu 2 sine theta 2. Okay, at point B, how will I write it? Mu 2 sine theta 2 is mu 3 sine theta 3. Okay, and at point C, I will write it as mu 3 sine theta 3 is mu 4 sine theta 4. Now, do you see the connection? When you combine all of them, okay, if you combine all of them, what you can write? You can write like this: mu 1 sine theta 1 is mu 2 sine theta 2 is mu 3 sine theta 3 is mu 4 sine theta 4. Okay, pretty much clear, obvious. Now the next thing, instead of writing, so I have many mediums, all of them are parallel. Light enters from one medium, goes to the other medium, one after the another. All are parallel mediums. Parallel, that is very important. Only then this relation will hold. Only then this angle will be same as this angle. Now, I am given some angle here. I want to find the last angle here. So I do not have to really worry about what is happening in between. I can directly compare these two. So instead of worrying and finding the angles, the intermediate angles, I can directly write my Snell's law between the starting point and the end point here. Okay, I can write Snell's law between any 2 points. Okay, I can directly write between A and C directly. Okay, mu 1 sine theta 1 is mu 4 sine theta 4. Okay, if mu 1 is equal to mu 4, then sine theta 1 is sine theta 4, theta 1 is theta 4. These two angles are going to be same. Okay, this light is making what angle with this normal? This is my normal. This also is my normal. Both lines are parallel. The normal here and normal here, both normals are parallel. The incident light is making what angle with normal? What is this angle? This angle is theta 1, same as theta 1 here. And this is making theta 4. Now, if theta 1 and theta 4 both become same, that means both this line, incident light and final emergent light, both are making same angle with this normal. That means both are parallel. It will come out parallel. Okay? So that's what we proved it here. Now, what is the angle of emergence in the last medium? So I don't have to worry about the intermediate mediums here. I can directly write Snell's law between this point and this point. Okay, let's say that this is the final angle. Okay, do not worry what is happening here. You write to Snell's law between this point and this point. What it is equal to 1 and sine 45 is equal to, this is root 2 and sine e. Okay, so 1 over root 2 is root 2 sine e. Sine e is half, e is 30 degree. That means this light is going to finally come out in this medium at angle 30 degree. Like this. Okay? That's it. So what will be deviation? What will be net deviation? Can you find out? What is net deviation? What is net deviation? You do not have to worry about the deviations here. Okay? You just worry about this initial direction and final direction. Initially the light was making what angle? 45 degree. This is 45, this is 45. So this is 45. Finally, it is making 30 degree. Okay? So I have this direction. This is the initial direction. Initially, it is making 45 degree, and finally, it is making 30 degree. Okay? So what is deviation? What is deviation? Deviation is 15 degree clockwise. 15 degrees clockwise. Okay? Got it? Okay, now a very interesting and important optical phenomena. Very interesting and important. Okay, it's like this. It is called critical angle. Critical angle, let's say theta c, and total internal reflection. Okay, TIR, let's say, I can call it as TINR. Total internal reflection. Reflection, okay? It is total internal reflection, okay? Let's try to understand. The first point, and the point that I have to remember, I have to keep in mind, okay? It is that it happens. What happens? Total internal reflection. It happens. Okay. It happens when light enters, or light not enters, light goes from denser to rarer medium. So this phenomena, which is known as total internal reflection, and it has to do with critical angle. both are related. We will see what is the relation and what is the meaning also. It happens only in this case. When light travels, it goes from denser to rarer medium. This is something that you have to remember, you have to keep in mind. Whenever light goes from denser to rarer, from water to air, from glass to air, okay, there will be a chance of total internal reflection. It does not always happen. It does not always happen. It happens, okay, it happens under certain specific conditions. Specific conditions. Okay. What is that specific condition? Okay. Angle of incidence. Angle of incidence is more than critical angle. Okay. I is more than theta c. Only in that case this phenomena will happen. When angle of incidence is more than a certain angle, which is known as critical angle. It depends on mediums. Let's see. First of all, let's try to understand the critical angle. Okay. Let's say that I have one medium here, mu1, and this is mu2. Mu2 is more than mu1. Mu2 is less than mu1. That means this is denser medium, denser, and this is a rarer medium. What we are going to do? We are going to understand this critical angle and total internal reflection. You also try to understand it very, very carefully. It is very simple. Very simple. Okay? You understand it once, you understand it for your lifetime. You are never going to forget it. Okay? Provided you understand it the first time. Okay? Now, it's like this. Okay. Let's consider one light ray here. This is one light ray. Let's say it is 1 here. At this point of incidence, I will draw a normal here. This is my normal. Okay. This is the original direction. What will happen when the light goes? What happens when light goes from denser to rarer medium? It bends away from normal. This is angle of incidence I. This is my normal. Angle of incidence, angle of refraction will be more than this. This becomes my angle of refraction. Angle of refraction R is more than I. Okay, light 1, this is also light 1. Okay, pretty much obvious, nothing much to explain. Now, what happens if I keep on increasing, I start increasing my angle of incidence? I start increasing my angle of incidence, okay? Angle of refraction also increases. This is light ray 2. Now the angle of incidence has increased. Angle of refraction will also increase. Makes sense? I keep on increasing angle of incidence, angle of refraction increases. For one particular angle of incidence, at one particular angle of incidence, remember, at one particular angle of incidence in denser medium, angle of refraction becomes 90 degrees. That angle is known as critical angle. That angle is known as critical angle. Okay, so this angle here, okay, this angle will be known as critical angle, theta c. Critical angle. The angle in denser medium, for which angle of refraction in a rarer medium, it becomes 90 degree. Okay, this is 90 degree. 90 degree, then that angle is known as critical angle. Remember this, note it down, memorize it. Okay. Not only that, what will happen after that, if I keep on increasing my angle of incidence, okay. Now, if the angle of incidence is more than critical, angle of incidence is more than critical, then what will happen? Then light will not go into the other medium. Light will not go into the other medium, it will come back in the same medium. And okay, it will come back in the same medium. This is 4. Okay, and then it will start following laws of reflection. It will not follow Snell's law. This is known as total internal reflection. When angle of incidence is more than critical angle, then light comes back in the same medium, same denser medium. It is reflected. This interface starts acting like a mirror, a plane mirror. Okay, mind it, a plane mirror. Light cannot enter into the other medium. It is going to come back in the same medium. The light is reflected. It is reflected back in the same medium. And it follows laws of reflection. Okay. In TIR, it is laws of reflection is followed. Okay, what is this? I is equal to R, not the Snell's law. Not the Snell's law. Okay, that is mu1 sine theta 1, mu1 sine I is equal to mu1 sine I. This is not followed. This is Snell's law. Snell's law is applicable as long as there is refraction, as long as the light enters into the second medium. Okay, so Snell's law will be applicable here for the first light. It is applicable for the second light. It is also applicable for the third light because this also is refraction. Okay, but here the Snell's law is not applicable. What is applicable? Laws of reflection. Laws of reflection. That means these two angles are going to be same. Okay. So now, how to find critical angle? So mu1, I will write like this. Mu1 sine theta 1 sine theta c is going to be equal to mu2 sine 90. Critical angle, okay? Critical angle. Theta c is angle in the denser medium corresponding to which angle in the rarer medium becomes 90 degree. That is critical angle. Okay. So what is this? Sin theta c is equal to mu2 over mu1. This is critical angle. Okay. And there is one very easy way to remember this. Okay. Sin theta c. Sin theta c. Mu2 is mu of the rarer medium. Rarer over mu of denser. Mu of denser. Okay, and then one very easy interesting property that you can relate this with, sin theta c. Theta c is critical angle. Sin theta c. Sin theta c is always going to be less than or equal to 1. Always. That means this value here should be less than 1. Always less than 1. Okay, and this rarer by denser, it is going to be less than 1. That's how you can relate these two things and remember it easily. Okay. Okay, alright. Now, condition. Now, if angle of incidence is less than or equal to critical angle, then refraction, okay, Snell's law followed. Snell's law is followed. Okay, if I is more than critical angle, more than, okay, in that case, okay, reflection. This is known as total internal reflection. Okay, laws of reflection is followed. Snell's law not followed. Snell's law not followed. Okay, then what is followed? Laws of reflection. Laws of reflection is followed. Okay, this is about critical angle and total internal reflection. Okay, let's do a few problems. Okay, there are many interesting phenomena associated with this phenomena, total internal reflection. Okay, we are going to look at all of those phenomena through problems, and we will discuss them also. Okay. It's like this. Question: find critical angle for following interfaces, or following pair of mediums. Okay. First, okay, air, water. Second, air, glass. Third, glass, water. Okay, let me write some values. Mu air is 1, mu water is 4/3, and mu glass is 3/2. What do you think? Can you find out? Can you find out the critical angle? Critical angle depends on pair of medium. Okay, it should be very easy. Once you remember this, sine of theta c, rarer over denser, you are going to solve all the problems. Okay, try to figure it out. Okay, it's like this. Air, water. Let's look at this. Air, water. This is air, this is water. Critical angle forms in denser medium. It is the angle in denser medium. Okay, for which angle of refraction in rarer medium, this is the rarer medium, it becomes 90 degree. Okay, this is known as critical angle. I will write like this: mu water times sine theta c is equal to mu air times sine 90. That's it. I have this answer. Okay, so what is sine theta c? Sine theta c is mu air over mu water. Okay, so this is 1/4/3. This becomes 3/4. That's it. This is my answer. What is critical angle? It is sine inverse 3/4. That's it. I could have get the same answer directly applying this relation, rarer over denser. Let's apply that. In case of glass, okay. In case of glass, air, glass. Okay. Sine theta c. Rarer. Of these two mediums, which one is rarer? Air is rarer, so I will write rarer over denser. This is 3/2. It becomes 2/3. Okay, so theta c sine inverse 2/3. This is not a standard angle. Okay, I will report it like this only. That's it. Now, water glass. Okay, this is 3.3/2. This is 4/3. Okay, this is 1.33. This is 1.5. When you compare these two mediums, air, water is denser. Okay, But when you compare water with glass, then water becomes rarer. It becomes rarer. Water is denser only here. When you compare it with air, when you compare water with glass, water becomes rarer and glass becomes denser. What will be sin theta c? Rarer is 4 over 3, denser 3 over 2, it becomes 8 over 9. Theta c, sin inverse 8 over 9. Okay, understood? It should be easy, okay? Okay, question. I have two mediums. Let's say that mu1 is 2.5 and this is mu2 is 1.5. Let's give it that way. Okay. This is my angle of incidence. So a light is traveling in this denser medium. It hits this interface which is separating it from a rarer medium. Now the question is, okay, find I max, that is the maximum value of this angle of incidence, okay, such that light enters into other medium. Okay, try to find it. Okay. Next question is like this. Mu is equal to root 2 and this mu is equal to 2. Okay. This is theta. Okay. Find net deviation if theta is equal to 30 degree. Theta is equal to 30 degree. Okay. Theta is 45 degree and theta is 60 degree. What do you think? What is going to be net deviation? Okay. Let's try to answer this. Keep it in mind. Whenever light goes from denser to rarer, look at the problem. Okay, look at the problem and try to recognize this. And once you are able to recognize, then this problem is a case of light going from denser to rarer. Then the first thing that should come to your mind is critical angle and total internal reflection. Try to understand this. First thing that should come to your mind is critical angle. Okay. What will be critical angle for this interface? Okay. Sin theta c is mu rarer over mu denser. Okay. It is 1.5 over 2.5. This will be 3 over 5. Sin theta c is 3 over 5. Okay, what will be theta c? It becomes 37 degree. Now, okay. Next is what it means. This is the critical angle for this interface. I want my light to be transmitted into the other medium. I want my light such that light enters into other medium. I want my light to enter into the other medium. What should be angle of incidence? It should be less than or equal to critical angle. For this to happen, angle of incidence should be less than or equal to critical angle. Okay, that means I is less than or equal to 37 degree. So that is what is I max? I max will be 37. I max is 37. Okay, maximum angle. If my angle is more than this, if the angle of incidence is more than 37, if it is 38, 39, 40, 45, it is not going to enter into the other medium. It is going to come back. That will be total internal reflection. Okay, here also. You see here also. And then the second problem. Okay, in this problem here, what will be critical angle sin theta c for this interface? It is going to be equal to root 2 over 2, 1 over root 2. Okay, so what is theta c? It is 45 degree. Critical angle is 45 degree. I have to find a deviation. Now, corresponding to each angle, what will happen? Okay. This is less than critical angle. Then this is equal to critical angle. Both cases. These two is equal, less than or equal to theta c. This angle here is more than theta c. Here total internal reflection will happen. Okay. So I can apply Snell's law for these two. Snell's law. I don't really have to apply Snell's law for this, because this is equal to critical angle. This is critical angle. Okay. So corresponding to this, angle of reflection is going to be 90 degree. I already know this. I know that here reflection is going to happen. I just have to apply Snell's law for this angle, 30 degree. Okay, let's do that. Okay, this is 30 degree. 30 degree. This is mu is 2. This mu is root 2. I will write 2 and sine 30 is root 2 and sine theta. Okay, in this other medium. So this becomes 2 and half is root 2 and sine theta. Okay, so sine theta becomes 1 over root 2. Theta is 45. It is more than 30, of course, because the light is going from denser to rarer. It will bend away from normal. Okay, so this is my original direction. Original direction. Now it bends away from normal, goes like this. Okay, so this is the deviation. That's what I want to find out. Deviation. Okay, this angle here is 30. 30, 30. And this angle we just calculated. This is 45. What is deviation? 45 minus 30. It is 15 degree. That's how we do it. You understand it? This is critical angle. So angle is of course going to be 90. Okay. Snell's law will be applicable. Snell's law is applicable. You see. Okay. You can write this directly. You can directly write it because this is critical angle. So angle of reflection is going to be 90. Okay. But you can find it using Snell's law also. Okay. You can apply Snell's law also. This is 45 degree. This is 45 degree. This is mu is equal to 2. I will write 2 and sine 45 is root 2 and sine theta. Okay. This is 2 and 1 over root 2 is root 2 and sine theta. Okay. This becomes root 2, gets cancelled. Okay. Sine theta is 1, theta is 1. Okay. I knew this answer even before solving it, because this is a critical angle. That is the meaning of critical angle. Angle of reflection becomes 90. Light goes like this. Okay. Now, is this reflection or refraction? This is refraction. The light just enters the other medium, and it follows a Snell's law. That means it must be refraction. Refraction. It appears as if the light does not enter into this medium, so it should not be refraction, but it is refraction, because it follows Snell's law, the biggest proof that it is refraction. Okay. So we say that light just enters. Okay, or it is just saved from entering. It just enters or it just avoids entering. Both happening together. Light passes through the interface, along the interface. Okay. Third case, angle of incidence is more than, okay, this angle of incidence is 60 degree. Angle of incidence is more than critical angle. Critical angle is 45. Angle of incidence is 60. So it is not going to follow Snell's law. It is not going to enter the other medium. It is going to be reflected. It will reflect like this. Incident light, and this will be reflected light. It will follow laws of reflection. This is 60 degree. This is the original direction. What will be deviation? This delta, 60 degree. Delta is 60. Okay. Now, if you apply Snell's law, you start getting garbage values. For example, try applying this. Okay. So this is mu is 2. This mu is root 2. So 2 sine 60 is root 2 sine theta. Okay. So 2 root 3 over 2 is root 2 sine theta. Sine theta is root 3 over root 2. This is more than 1. This is not possible. So reflection is not possible anyway. For reflection to happen, this theta should be, sine theta should be more than 1. Okay, makes no sense. Not possible. Okay, so this is internal reflection and critical angle. Okay, we are going to do many problems, okay, based on this.